Okay, hello everyone. Welcome to this lecture. So this is Hua Qu. I'm a postdoc in Chelsea Lab. Today I will give the lecture about domain generalization. So before we start, I will first go through some logistic things. So the project milestone is on Wednesday, and the homework 4, which is an optional homework, is due on Monday. Here is the plan for today. Today I will introduce a new concept called domain generalization. I will first do some problem statement and problem formulation, and then introduce two kinds of representative algorithms. The first one is to adding explicit regularizers to solve this domain generalization problem. And the second one is we can leverage some data augmentation to handle this problem. And the goal for this lecture is that I will first let you know how to understand the intuition behind the domain generalization and the problem formulation. And I will also see that you can be familiar with the mainstream domain generalization approaches, so the regularization-based approaches or augmentation-based approaches. So let's first do some recap about the domain augmentation that we learned from our last lecture. So in the domain adaptation, we aim to use some training data from the source domains and make it perform well on the target domain. This is a kind of a form of transfer learning, but we can also access to the target domain data during the training process. So it is transductive learning. So we have the training domain data and the unlabeled target domain data, and we want to perform well on the target domain. So there are two common assumptions for the domain adaptation. And the first one is the source domain and the target domain only differ in domain of the function. So it means the conditional distribution py given x is the same between the source and target domain. And there also exists a single hypothesis with low error on both source and target domains. We also do some revisiting to see that a domain is a special case of task. So a task is composed of three components. The first one is Pix, is for the marginal distribution or feature distribution. Another one is for the distribution of the domain of the function, the py given x, and also the loss function. So for one task that we learned from the multitask learning or meta-learning, all these three components can be changed from different tasks. But in the domain, only the Px can change over different domains. So before we start, then we will mention that can we always access unlabeled data from the target domain? However, in some real-world applications, because of the following two reasons that we cannot always access this target domain. The first one is sometimes we want to do real-time deployment, and we do not have time to collect enough target domain data and to do the adaptation, including domain adaptation or collect labeled data to do some meta-learning or few-shot learning adaptation. And in the case that obtaining the target data may be restricted by the privacy policy. And I will provide some examples for each of these reasons. The first one is for the real-time deployment. And in this case, for example, if we want to train an autonomous driving system and we want to let these models train on 3 types of roads, and then we want to deploy this model to a new road. For example, we want to deploy this on the night. And in this case, we want to do some real-time deployment, and we do not have sufficient time to collect enough data. And another case is about another example is about the privacy concerns. So there are a lot of policies about the privacy concerns. So for example, the most famous one is about general data protection regulation, which is from Europe. And in this case, we cannot share data between different institutions or hospitals or any other stuff. And for example, if we want to build a disease predictive model, so this disease predictive model, we train it on the 3 hospitals. For example, hospital 1, 2, 3. And then they want to deploy this model to a new hospital. And in this case, to deploy this model to a new hospital, we cannot access the training data due to some privacy concerns. Based on these two things, I will first to mention why we need domain generalization, and first give some formal problem formulations for this. In domain generalization, so assume we have a bunch of source domains. For example, there are 3 domains, the clipart, painting, and sketch. We want to recognize different objects for each domain. And we will train a model, and to get such a neural network, this is regarded as a trained model. And then we will deploy this model to some on-Z target domains. Here is a domain for the real image. And we want to generalize some common knowledge from these source domains and to make its models perform well on this target domain. Mathematically, the domain generation problem could be formulated as we given a bunch of source domains P1x1 to Pnx1. We aim to solve on-Z target domain Ptxy without accessing the data from it. So similarly, there are also 2 common assumptions. The first one is all domains only differ in domain of the function. It means that the conditional distribution Py given x is the same across different domains. In our previous definition of domain adaptation, we will make the conditional distributions to be the same between the source and target domain. But here it will be exactly the same across all domains. So only Px can change. So another assumption is that there is a single hypothesis with low error in all domains. So that what guarantees that we can learn a model that can perform well across different domains. Okay, so this is also relating for the domain, the special case of a task. So it's also hold in the domain generation problem. Based on this definition, I will try to do some comparison between the meta-learning that we learned in a lot of lectures before and the domain generation. And in meta-learning, it is kind of like transfer learning, and we want to transfer some knowledge with many source tasks. So given the data from task 1 to n, we want to solve a new task T more quickly, proficiently, and stably. And in domain generation, this is a special case of the meta-learning that we learned before. So given the data from domain D1 to Dn, we aim to perform well on the new domain dt. So, but there are 2 kinds of difference between the domain generation and the meta-learning. The first one is only Pix changes across different tasks. But in the meta-learning, we can change a lot of things. So about 3 components. And in domain generation, we want to directly generalize to the new domain instead of doing any kinds of adaptation. Yeah, this is basically the comparison between meta-learning and the domain generation. And the second comparison is between the domain adaptation that we learned from our last lecture and domain generation. In the domain adaptation, we can access label data from all source domains, and we can also use unlabeled data from the target domain. So we aim to make the model perform well on the target domain. And in this case, the target data, we can access the target data during the training process. So we can access the unlabeled data, and which also distill some information of the target domain. And in domain adaptation, there are only 1 source domains typically. So, but people can also use more source domains, but we can only rely on 1 source domain to achieve success domain adaptation. And the model trained for the domain adaptation is only specialized for the target domain. So it means we only care about the performance at the specific target domains that we can access, instead of consider this problem on a more general case on a bunch of domains. So domain adaptation is one kind of like a transactive learning setting. In domain generation, the things would be a little bit different. So in domain generation, so given label data from a set of source domains, P1x1 to P1xy to Pnxy, and we aim to make the model perform well on the target domain, a bunch of target domain actually. So we cannot access the test data during the training process. So this is the first difference. And the second one is domain generation usually needs more than 1 source domain. So if when you have a bunch of source domains, you can capture the common knowledge behind these source domains, and then to generalize this common knowledge to benefit the performance of the target domain. And the third difference is that these models can be applied to all domains, including the source domains and the target domains, and even some domains that we didn't capture. So this is why we need to learn some well-generalized knowledge and can be generalizable to a bunch of domains. Yes, this is the key difference between the domain adaptation and the domain generalization. In this lecture, we want to mention, and domain generalization is an inductive setting. Okay, so based on this definition and based on some comparison, I would like to show you some real-world applications of domain generalization. The first application is about sustainability, and we want to do some wildlife recognition. We would like to recognize different animals on different locations. So here we will use, for example, here we have 245 locations, and we want to train a model from these locations and to generalize these models to new locations. Another example you may be familiar with, because in the last lecture, we also see the domain adaptation version of this tissue classification example. So we aim to classify one tissue image, whether it's normal or it's tumor. So basically, we learn a model from a bunch of hospitals, and then we train this model to some new hospitals. Here is Hospital 4 and Hospital 5. And in the domain adaptation, instead, we probably only have 2 hospitals, and we want to learn some common knowledge from these 2 hospitals. The third application is molecule property prediction. The molecule property prediction is quite important in the drug discovery field. So they want to predict some toxic of given a small molecule, we want to predict the toxic. And we train a model on different splits of these molecules on different scaffolds. And then we aim to generalize some common knowledge and to make it work on some unseen scaffolds. And the last one is about code completion. This is also very important applications, for example, like in the field of programming language. So we have a bunch of reports, and then we train a model to predict the next tokens in the context of source code, and then we aim to generalize this model to some test distribution. Okay, so this is the basic introduction of what is domain generalization and do some comparison and give some applications. Next, I will introduce some specific algorithms about for domain generalization. The first one is we aim to add some explicit regularizers to handle this problem. So before we dive into the specific algorithm, so let's first think one problem: how to learn such a generalizable representations. And to answer this question, a natural way is we want to think another problem is about why do machine learning models fail to generalize? Here is one very simple example. So our goal is to classify dog versus cat. So there are 2 domains. The domain 1 is water, and the domain 2 is grass. And we actually have 4 groups. So the first one is dog in the water, and a cat in the water, and dog in grass, and a cat in grass. So for dog in the water and the cat in grass are 2 majority classes, 2 majority groups. And otherwise, cat in the water and dog in grass are minority groups. Based on this, we train a model on these 2 source domains, and get a trained model, and then deploy this trained model to a new domain. For example, the dog in the forest. And our question is this a dog? Our human can easily to recognize this as dog. But for computer, it is very hard. So usually in computation, it's very easy to recognize. But in this case, it's hard to recognize this as dog. And the computer will make the wrong prediction. So why this happened? So there are some similarities in the training data. We can see the dog in the training data, the dog usually in the water and the cat usually in grass. And then it sees some similar environments compared with grass. And then the grass would be a sparse information. It means that these models will sparsely associate the cat information and the grass information. And that's when the computer sees some similar environments, it will make wrong prediction. So our goal is to cancel out such sparse information here. And to do this, we aim to train a neural network to learn some domain invariance. So this is another concept I want to mention here. So the domain invariance is that we want to learn that a bunch of features via the neural network that don't change across different domains. In case that we can learn such domain invariant information, for example, we can associate the animals with the labels. And the computer can make the right prediction. Okay, yes, this is something about domain invariance. And based on this definition, I will then detail the regularization-based method. The key idea of regularization-based method is that we want to use a regularizer to align representations across different domains and to get the domain invariant in representation. Let's still back to this example. So we have two domains and the two classes, and the two classifiers, the cat and dog. And in this case, we can get the representations, for example, for domain 1. And for domain 1, we can get the representations, which is composed of two information. The first one is animal, and the second one is water. So we only cover some major informations in these images. And similarly, we can get the representation for domain 2. So it's also animal and grass. And I hope we can align these two representations to enforce them to be very similar. The simplest way to get a smaller loss is that finally this neural network can only learn the animal information because the animal information is shared across different domains. Okay, so based on this example, I will then mathematically define some generic loss function for that. So this is a typical loss function for the regularization-based method. In the first term is for label classification loss. For example, in this, we classify dog versus cat here, and then we will average the loss over all training examples. And then we will define an explicit regularizer to learn the domain invariant representation. This is the key part for these regularization-based methods. So how to define such a regularizer. Okay, so before we dive into this to give some specific algorithms, I will first recap the domain adversarial training in domain adaptation that we learned from the last lecture. The key idea is that the prediction must be made based on the features that cannot be discriminated between the domains. For example, given one image, this is an input X, we will feed this image to our feature extractor and get the features. And then we have two branches. And the first branch is to do the label predictor. And we aim to make accurate label prediction. So in this case, because in domain adaptation, we only have the labels for the source domains. So only data from the source domain are fed into this branch. And second branch is our domain classifier. The domain classifier, we aim to make this image we cannot predict the domain for this image based on these features. So in this case, the features, we can learn some domain invariant features. So both data from source and target domain can feed into this branch because we want to do some domain classification here to classify whether this feature is from the source domain from the target domain. Okay, I now have one question. So this is a very simple version for the adversarial training in domain adaptation. So does anyone have ideas on how to use the domain adversary training in the domain generation setting? So any volunteers?
You want your adversary to predict which domain are you in?
Real or for each image? Yeah, you want to predict its corresponding domains, you mean?
You want to predict if this is the water or not, for example.
Yeah, that's right. So, yeah, there's something that we will mention here is we have the label predictor and the domain classifier. And instead of we only feed the data from the source domain into the label predictor, in the domain generation settings, we will feed data from all source domains into this label predictor, so to predict its corresponding labels. And similarly, all the data from all source domains will be fed into the domain classifier. And instead of to classify whether it's from source domain or target domain, because there are no such a definition in the domain generation settings, we will to predict those domain labels for every image. Okay, based on this definition, so I will first mathematically give some definitions for this label predictor and the domain classifier and its corresponding losses. And in the label prediction, we aim to do such a label prediction, give the input x, and we will extract some features from f theta x. And then we will do the label predictor to get its predicted value with the function g. And we will sum it for every examples, finally to optimize the function, the parameters of label predictor and the feature extractor. And here, the smaller is better because we want to make accurate prediction in the source domains. For domain prediction, instead, we want to predict these domains, but we actually want to maximize the loss. So the larger loss is better because the larger loss means it is harder to distinguish domains for average input examples. In case when we cannot distinguish domains, we can learn some domain invariant features and to make it generalizable. Okay, so, and then we will bridge from the generic formulation and the new formulation for the domain adversarial training in domain generation. This is a loss for DNN loss in domain generation. So the first term would be label classification loss. And the second term would be we will design one regularizer to learn such a domain invariant representation. And the four algorithms has 4 steps. The first one is that we will randomly initialize the encoder, the label classifier, and the domain classifier. Then we will try to use the domain classifier loss, the LD, to optimize the domain classifier. And we will, based on these results, we will update the label classifier and the encoder by considering both label classification loss and the domain classification loss. We will finally repeat the step 2 and step 3 until convergence. Hello?
So about the second step in the foot algorithms. Are we trying to optimize the domain classifier to perform very well or perform very poor?
Perform very poor.
Because I'm thinking about if you want to do the adversarial training, right? You should have a very good domain classifier, so But then it will force the representation to be domain invariant.
Yes.
Then in this case, shouldn't we like make the classifier very good so that then it forces the similarity?
You mean good is like in case you cannot force the classifier. Oh yeah, this is good. Yeah. So in case you can maximize the loss, so you can learn a good domain classifier, and the image can force the domain classifier.
Yeah, this shouldn't it should not be the negative sign in front of the loss function. Then.
Because we want to maximize this, so this is the minimize one. Yeah. Any other questions?
Do you think this would be more expressive or less expressive than, say, learning features for a domain and then, so like a multitask setting, and then conditioning on the domain with the feature extraction for the label?
So your question is you want to learn a separate directions or?
So you learn some features for each domain,
Yeah.
and then you condition on those features for the label classification. Would that be equally expressive?
Okay, I see. So you mean you will use separate encoders, and every domain have one encoder, right?
Yes, sort of like extracting features for the domain, and then training the label classifier.
Possibly, in some cases, it's more expressive. In case when you have a lot of data from every domains, so you can learn a better encoder without sharing encoder with other domains. But in some cases, you cannot collect so many data for every domain. So in case you would like to share some representations and to have a shared encoder, yeah.
And what happens if we don't have information about the domains? Like we have a data set and it's not labeled over domains.
Yeah, this is a very good question. So this is something that we also try to learn. So without considering the domain information, there are a few solutions. The first one is you can try to predict the domain information based on the data. And in some cases, if you train an ERM, empirical recommendation, you can also distill some domain information and to see whether you can predict it well. Other case, you can find that some misclassified examples, this may be from the minority domains, and you can upweight these examples and to make it work.
Thank you.
Okay. So, questions? Yeah.
So one question was, I've seen papers who try to learn shared latent representation between the tasks or domain. And so you learn task specific, like domain specific, and the domain common, like the shared feature space. So how does it relate to so would that perform better, or would this kind of algorithm perform better?
To repeat the question, so you mean we
Separate domains.
different domains, each domain has its own encoder?
Yeah. So you learn domain-specific parameters
Yeah.
and shared parameters across the domains. By maximizing information between the different domains present, between the samples that you have. So you can learn the common latent representation.
Yeah.
And also
And you have two branches.
Yeah, two branches to learn the some have some domain-specific layers. Yeah, I think this is possibly more expressive. It's the same question, and
I think wouldn't it give you more expressive power in the testing time? Like let's say if you just want to output particular feature of particular domain.
But in the test time, you will definitely get one new domain, so you do not have its corresponding branch.
But we could use the common latent representation.
Yes.
Yes. In case you mean you want to abandon the domain-specific branches.
We could use the common
Common ones, and for how to do it for the domain-specific ones, I just want to clarify your question. So probably I can use some whiteboard. So you mean there are one shared representation, this is shared, and then you have two branches for two domains. And how to do it for the test? So in the test, you definitely need to go one of them branches. Yeah, but you do not have the information for the test time, which branch do you want to go.
But can't we, no, I was not thinking about that. I was talking about learning common latent representation for the samples themselves.
For this one?
Yeah, so assuming that that's a latent space,
Yeah.
we could learn a common latent space and the shared latent space. And then we could use the common latent space to then generate the even any for any domains.
Yeah, I think this is what we learned right now to use a shared encoder for every domain. So let's go back to this one. So we have a shared feature encoder and to go to every domain.
Do we have any conditioning over the latents that we learn over the shared?
We currently do not add any conditions, but possibly add some conditions to enforce this would be helpful.
Would multitask learning helpful here?
For the multitask learning, the key point is that multitask learning only solves when the training domain is exactly the same from the test domains, right? But we want to solve some unseen domains. Okay. So any other questions?
Sorry, what if you don't have a bunch of domain labeled data? I mean, maybe with the cat-dog example earlier, you don't know that grass and water are really two different domains and are going to be a problem until after you try to do it.
Yeah, I think this problem is that I mentioned, so probably you can see, try to distinguish the domain information and to do the domain prediction. And then in other case, you can see that how to, for example, how to see that you have to feed the model into ERM ones and to identify the misclassified ones. These ones may be from the majority, from the minority domains, or from the minority groups. Yeah. Okay. Okay. So, let's continue. So domain adversarial training, so leverage adversarial optimization to learn the domain environment features. So you may ask, are there any other ways to do that? Then I will introduce one alternative approach called Coral. In the Coral, so the key idea is that it can directly align the representations between the different domains with some similarity metrics. And in Coral, so which is called the correlation alignment for domain adaptation, although the name is from the domain adaptation, and this method is originally from the domain adaptation, but it is usually also used in domain generalization in recent years. So here I will only choose the domain generalization version of this algorithm. So in this one, assume we have two domains. For example, here we want to recognize different objects. We have some shared layers, and this could be regarded as a feature extractor. And then we will use features to feed into some classifier to get the classification loss for every domain. So for the domain 1, we have one classification loss, and the domain 2 has another classification loss. Then we will have the Coral loss. In the Coral loss, we want to directly align these both representations. Before we dive into the Coral loss, I will first give some notations. So the notation x1 is a feature metric, and for the representation, and this is with dimension n1 times k for the domain 1, and the x2 is similarly for the domain 2 is n2 times k. And the k is the number of features here, and we get the mean value with this formulation, and with dimension 1 times k, and similar to the mean value of the another domain over all examples. Then we will try to calculate some covariance metrics in corals. The goal for Coral is to make these covariance metrics exactly similar to control the similarity between different covariance metrics. So in the covariance metrics, this is something that we learned from some math courses, so to get these covariance metrics. And finally, define one Coral loss to make this covariance over features would be very exactly the same. And this is also the loss for the Corel algorithm. And we will combine the classification loss for the first time over all different examples. And we will also design one Corel loss to explicitly regularize to learn the domain invariant representation. So the key idea for the Corel, behind the Corel, is to make the covariance matrix similar for every domains.
Is this extendable to more than 2 domains?
Yeah, it's extendable. So you can directly add more domains, for example, domain 3, 4, 5 with one classification loss and use pairwise Corel loss to do that.
So do we have individual encoders for different domains?
Typically, people will share the encoders. Yeah. Any other questions?
So my question was in general about how much does model architecture and our mathematical formulation of the problem matter in this kind of in approaching this kind of problems?
So you mean for the in generic version of
Everyone.
regularization?
So in general, for domain generalization or any particular this kind of problems, while approaching how does choosing a model architecture
Okay.
and mathematical formulation of the problem helps?
So it depends. So like we can increase the model architecture from ResNet or even for visual transformer, you will have more parameters and these models will be more have strong express power and to represent more information. And designing some regularizers is also very sensitive in these specific domain generation problems. In case you have very large models, in case you have the same models, same backbone, and we can compare different kinds of regularizers. And with the same regularizers, we can compare different backbones.
Maybe I want to understand the limits of each of this. So how much the model architecture selection affects your performance, and how much can the mathematical formulation of loss term or any of that term would affect the performance in general? Like how much power do they have while
I see.
So for each of them, so for model architectures, for the comparison between model architecture and the loss function, right? For different data sets, I think increasing the model, the express power of model architecture is not a bad choice. So you can definitely improve the results. But typically we try to add one regularizer, and this chosen regularizer can affect the problem, the performance more. If we found a bad one, so it even hurt the performance. Yeah, because if you increase the model express power, so the performance of ERM will also increase. Yeah.
Actually, can you talk a bit more about the motivation behind aligning covariance matrices as opposed to
In case if we can align different kinds of different order of the information, it would be helpful. So the simplest one, you can directly align the representations. And in these papers, they consider the second order versions of covariance. So if you can do more, but if you can do more, you will have like more cost, computational cost to do more. Yeah. Okay, so we can continue. And then for the results, I just choose some results from the Office Home, DomainNet, and the iWebCam. And in the Office Home, we have 4 domains, and we will hold one domain as a test and use another 3 training, another 3 domains as training, and then to generalize one model to the test ones. And we will repeat the progress for 4th. So for every domains to do some evaluation. And also we'll do the similar things for the domain net. And for the iWideCam, as I mentioned before, is basically we want to generalize the model to new locations to do the wildlife recognition. And we can see the auto performance well compared with EIN, and then sometimes hurt the performance compared with EIN. I think this solves the question that designing a suitable regularizer is very important. Finally, for this kind of method, I will mention some pros and cons. The good things is that the first one is these methods can generalize well to all kinds of data and networks. So for example, if we want to change it to graph data or text data, we only need to change the shared layers, the backbone from BERT and to graph neural network or any other layers. And there are also some theoretical guarantees here in these kinds of methods. I will not dive into this one, but if anyone are interested in any theoretical results, please email me and I can send you some papers to discuss this. But the bad thing is that these regularizers sometimes being too harsh or too constraining on the representations. As we can see that DNN cannot work very well in some data sets. And let's also go back to see why regularizer being too harsh. For example, in this one, we can go back to this dog versus cat classification. And this is the loss function. And if we directly add one explicit regularizer, that it will encourage the internal representations to only contain the no info about the background. But sometimes it's in the mixture, so we also need some informations to do this classification, or to, if we do not have any backgrounds, it even hurt us to learn a better domain invariant representations, or even hurt the express power of the neural network. Any questions? Okay. So based on this, we can see that in some real-world applications, like iWideCam, the core improves the performance, but in some other data sets like R1, this is a medical image classification task, so the core even hurt the performance. So that also hurt the performance, as I mentioned before. You may ask, are there any approaches to relax the dependency of the regularizer? Then let's move to our next part of the algorithm design, so to do the data augmentation. Before we detailing the data augmentation, let's first recap the spurious correlation. In the spurious correlation, our goal is to classify the dog and the cat, and the background is sometimes spuriously correlated with the animal, and the models cannot make a right prediction. However, there is one question. In case we can collect more data, so we have the grass data, the water data, and the car domain and the keyboard domain from both dog and cat. So we want to still recognize this dog. The question would be, will the network still associate dog with water background in some source domains? So any guys want to answer this question? So how many people think cannot associate it?
If you still, mainly still just have dogs in the water background, then it might still just associate dogs with water background and have to be correct.
Yeah, if we do not consider this scenario, so yeah.
There, consider whether there is like a uniform distribution
Across different backgrounds. In case we consider all backgrounds with a similar weight or.
Then maybe
Yeah, that's no. So because there are many more backgrounds, so we cannot recognize dogs only with the grass background. And in this case, the models can produce the right prediction. However, there is one challenge. In the case that we cannot always collect model data from the different domains. So what we want to do, we can aim to generate more data and to train this model. And here we want to introduce some methods for data augmentation. For example, there are some simple operators that can help us to generate more data. And in the computer vision, for example, given one image, this is the original image, we can use different operators to generate the data, like flipping, rotating, cropping, or like a PCA or edge enhancement, or any other methods that we can generate some image data based on one image. And in the NLP domain, we can do some back translation. In the back translation, we have one sentence originally from English, and then we want to translate it to French and then translate back. So the augmented example would be slightly different from the original one. And these data augmentations can typically help us to do the domain generation, can benefit the performance. However, these simple operators require the knowledge of the problem domain. For example, we need to see, oh, this is the image data or from or text data, or to adopt different strategies to do the data augmentation. Our question would be any general approaches. So I will introduce one general approach for data augmentation in this lecture. It's called mix-up. In the mix-up, the key idea is to interpret training examples. Assuming we have a learned model with the training data. So the training data has n examples with the input and the label pair, the x, I, y, and from I to equal to n to n, x equal to 1 to n. And we will train a classifier based on this training data. And then mix-up aim to replace this original training data from a mixed version. So in this case, we will have two examples, xi, yi, and xj, yj. And then we will do some linear interpolation, so also like a convex combination between the xi, yi, and between xi and the xj and the y and the yj. So and in this case, we can generate some virtual examples called xi tutor and yi tutor for both features and labels, for both input and labels. And then mix-up will use these generated examples to replace the original examples and use the new training data to build a classifier. So here is one example for the mix-up. We can generate some virtual examples between two classes. So the first, the image in the left-hand side is for the cat, and then next one is for dog, and we can combine them to generate some images in the between, so from cat and dog. So this image has around 70% probability to be classified as a cat and 30% to be classified as dog. So this is a very common and useful ways to do data augmentation. Any questions about the process for the mix-up? Okay. So in domain generation, mix-up itself can improve the performance of domain generalization. So let's see. Here we want to do the tissue classification from chameleon, and also to do some land type prediction. In the land type prediction example, we call this data set is called FMOW, and we want to, given one satellite image, we want to classify its land types, and we want to generalize from some year and region combination to other year region combinations. And compared with the ERM, and mix-up can improve the performance. However, it is not always good. For example, we will still use this R1 example. This is a quite challenging data set. So mix-up even hurts the performance compared with ERM. The key drawback for the original mix-up is that this method only focuses on the data augmentation instead of trying to learn some domain invariance. So the question is how to improve the original mix-up. To introduce the next algorithm, I will first give us simple examples with spurious correlation. So this example can help you to understand what happens in the next algorithm. And the example is quite similar to the examples from the real-world images. So this is a toy case. In this toy case, we have a lot of green 2s and red 5s. And our goal is the label 1 is to see this digit is smaller than 5, and the label 2 is this digit is larger or equal to 5. And we have a target domain with similar colors, or with green 5, but the green 5 is from a different ways, as background is green. And feed into a neural network, and this neural network cannot produce the correct prediction, because in the training part, the models spuriously associated the color with the labels. And so this example is very similar to the examples I gave before for the dog and the cat classification. Okay, so based on this example, I would like to introduce Lisa to improve the original mix-up. The key idea behind Lisa is Lisa wants to selectively interpret examples and to emphasize some invariant information, not only on the data augmentation like mix-up did. So this is like the examples. We call it colored MNIST. So we have some 2 majority groups and 2 minority groups. And based on the build upon the mix-up, there's one variant called intra-label Lisa. In the intra-label Lisa, we aim to interpret examples with the same label but from different domains. We just add one simple constraint on the original mix-up. So to make it, the domain is quite different. So from DI not equal to DJ, but we will make sure the labels are same. So YI equal to YJ. And we can see in these 5 images, the first one and the last one, I mean the left one and the right one is from the original data set. So lambda equal to 0 or lambda equal to 1. And then we can generate some images with different backgrounds. We can see these 3 images in the between. And all images are associated with the same label. So with digit larger equal to 5. And we can see that even when we generate a lot of different backgrounds, all of them associated with the same label. And in this case, the models will finally ignore this color information and only focus on the digit information and to capture this invariance. Okay. Any questions for this?
I think I have a mix-up question in general. So is it possible, have people been trying to apply mix-up to the text domain?
Oh, yeah. I will mention it later, yeah. Any other questions?
If you don't have labels, do you choose it based on how certain of the labels of the target domain?
You mean domain labels? Yeah, if we do not have domain labels, it's a little bit hard to apply this algorithm. But one simple solution is that we can try to see whether we can only mix the examples with the same label without considering the domain information. In this case, you can also generate some similar things for this variant.
Could you do that if the model is, let's say, confident on some target samples? Could we use those as a label ground truth?
You mean we want to train a model on the target samples?
Yeah. And, no, so we do inference on the target samples.
Yeah.
For which we don't have labels. But the predictions, if those have good certainty, like if the model is much more confident on the samples, of some samples.
Test domain.
On the test domain, yeah. Could we use them as a ground truth to get the
The question is like we can use labels from, you can some examples with some pseudo labels in the target domain. Yeah, this is another question would be close to some domain adaptation or semi-supervised learning settings. Yeah, we will not consider these settings here.
Is there data on how this performs on, out of either domain distribution? So like if you then show it a blue 5 and a blue 2, does it work better on those than if you had not done any red-green augmentation?
Your question is that if we have any like blue ones or any auto distribution, something like that. Yeah, it definitely works. So for example, we can put this example here, is we change the background from green to blue, so it can still work very well. So because in case you learn some digital information and you ignore this domain information. Okay, so another variant of LISA is called intra-domain LISA. In intra-domain LISA, it may be we add some constraint on the domain level. So we want to interpret examples with different label but same domain. So di is equal to dj, but yi is not equal to yj. And in this case, the left and the right ones are also from the original data set. All these are red 2 and red 5. And we can generate a lot of images in the between, but with different labels. So in this case, we can see even the domain information is the same, but all of them is associated with different labels. So the domain information is not the reason for the label changes. So we can also make these models exactly ignore this domain information and only focus on the environments, focus on the digital information. Any questions for this variant? Okay, let's move on. In practice, LISA aim to combine these both of them because each of them has its own like applicable scopes. The first one for the intra-label, it works better when there are more domains. Especially if you have more domains, you can have more combination to apply the intra-label LISA. And another thing is like the spurious correlations are not very strong. In our practice, that intra-label LISA works better. And instead, the intra-domain LISA works better when the domain information is highly spuriously correlated with the label. So in case, for example, this data distribution is quite imbalanced, and there are much more, even 99% of green 5s and red 2s. So in this case, that intra-domain LISA works better. And in practice, LISA uses one hyperparameter p-select to determine when to use intra-label LISA or when to use intra-domain LISA at each iteration.
What happens if, say you cannot apply either of these? So like, supposing you only have red 2s and green 5s. Okay.
Yeah, this is a very interesting question. We already investigate in our another settings. This is like, in this case, you can see that we call it like under specification things because these models can infer the labels based on the background information only or inform the labels based on the digital information. Right? We typically want to build models with two heads, and each head represents one kind of things. The first head maybe represent the domain information, I mean the color here, and also another head would be the label information by sharing some layers. And we will use some unlabeled data to make two heads produce quite a different output. And in this case, we can, when we have new domains and the models aim to classify the labels, we can try to collect a few examples to pick which head that we want to use. Yeah. Yeah, I can send you the paper. Please email me, and I can send my paper to you.
So, from like the previous lecture, we saw cycle gap. Would something like that be useful here for data augmentation?
CycleGAN could possibly use here. It is as powerful data augmentation methods. You can even use some to disentangle the representations and to shift something between different domains, and can even improve the performance. Yeah, but applying CycleGAN would be a little bit complex, so and need more efforts to tune all the hyperparameters.
Is there any reason that you choose either intra-label or intra-domain bonobos in the same iteration?
We choose either ones because each one have its own pros and cons. So in we actually in practice we choose intra-label Lisa more, but in some cases intra-domain Lisa can also work very well. Any other questions?
So for intra-domain, does it matter like which label pair you choose?
Yes.
Right?
Yes.
So how do we decide?
To choose which labels? Yeah. You randomly pick some examples. I will choose the 4 algorithm here. So maybe you can take a look what is the process. So in the 4 algorithm of Lisa is that first stage, we randomly initialize the model parameter theta, and then we will sample one strategy from a Ballooning distribution and with the hyperparameter p select. And we will sample a batch of examples B. Here, this is in this stage, we will choose either intra-label Lisa or intra-domain Lisa. So if S is equal to 0, and we will use intra-label Lisa, and for every examples within this batch, we will sample another example that satisfies yi equal to yj and di not equal to dj. And similarly, in intra-domain Lisa, for every example in the batch, we will sample one example that satisfies that the label is different, but the domain is the same. Then we will use we will interpret these examples and use the interpreted examples to update the model. Finally, we will repeat the steps 3 and 4 several times until converge. So for every iteration, we will choose either intra-label Lisa or intra-domain Lisa.
Could this be extended from, say, two classes or 2 domains?
Yeah. We can use in a bunch of domains or classes.
Like at one time, for one label, you take all domains and average over that?
You mean for the intra-label one?
For the intra-domain one.
For the intra-domain ones.
We will use, if we have more than 2 domains, and we will, for each examples, we will only pick examples with the same domain, but without considering the labels. Only make the labels are different, yeah. Any other questions for the process of the 4 algorithm? Okay, let's move on. And here we show some results to compare EIM, empirical risk minimization, and the Coral we mentioned as a regularization-based approach, and also Lisa, and we mentioned here, the augmentation-based approach. So the Chameleon is a 2-class classification, is a binary class classification, and with 3 training domains. And the FMW is around 32 classes, and a bunch of domains. R1 is around 33 classes, if I remember correctly. And Amazon is also a binary classification. Amazon is a text data. And in these 4 data sets, Lisa works better than both Coral and the EIM. And in the I1 camp, the Coral works better than other methods. Also in the OGB to do the molecule property predictions, that EIM even works best compared with the other method. So in this case, we can see different algorithms have its own advantages and disadvantages. And you may choose which one you want to use based on the experimental results in your practice. So you may also see that Lisa works well on the image data, but also works well on the text data. So how to apply mix-up in the text data, because it's a little bit weird if you apply the mix-up on the input level, so on the original text data. So here I will briefly mention the manifold mix-up. In the original mix-up, we apply the mix-up on the input and then get the mixed image and feed into the feature extractor to get the feature representations, and then feed this feature representation to the classifier to do the more classification. And in the manifold mix-up, we instead apply the mix-up on the input, we do the mix-up on the feature level. For example, in the text domains, we typically do it on the top of BERT, the output of BERT. So we will change the feature extractor as BERT and apply the mix-up on the features on the output of BERT. But in image domain, I use this example here. We have the dog features and the cat features. And we will apply mix-up here and get the mixed features. And then feed these mixed features to the classifier. Any questions for this one? Okay, so the final results I would like to show is some invariance analysis. So how to measure the invariance. So the direct way to measure the invariance is that when we get the representations, the invariant representations, we can try to use these representations to build a model. And like a logistic regression or any other models to predict the domains. And we will use the accuracy of the domain prediction to measure whether we can find a better invariance or not. Another metric that we want to show is that we will measure the divergence of the predictions among the domains. So we will leverage the representations or the predictors. The predictor means the logics to see that whether for every classes, we can see the divergence between every domains. We will have one distribution about the output, the representation distribution, and we will try to do some pairwise comparison among different domains, and then we will sum the results for every classes. So we compare Lisa with ERM, also with the Valina mix-up. The RM, IBRM, REX is other kinds of methods for regularization-based methods. And we do see that Lisa can lead to greater domain invariance than prior methods with some explicit regularizers. So both metrics, smaller value represents greater domain invariance. Any questions for this? Okay. And finally, I would like to also do some comparison between regularization-based versus augmentation-based methods. In the regularization-based methods, I will recap the pros and cons. The first advantage is that it can generalize to all kinds of data and networks and has some theoretical guarantees. But it relies on the design of regularizers. Also, sometimes the regularizers are too harsh. And in the augmentation-based method, it is easier to understand and simple to implement. And we do not need to worry about how to design very well generalizable regularizers. But sometimes it's largely limited to the classification problems, also some problem types if we want to apply some simple augmentation operators for text or the image data. Any other questions? Yeah, this is the plan for today. So we introduce the domain generation problem and give the different definition for this. And we introduced two kinds of algorithms. The first one to adding explicit regularizers in the loss function to align the representations. And the second one, we do some data augmentation to generate more data and to learn domain invariance. So hope we can reach the goal and to understand what domain generation is, and also to be familiar with major domain generation approaches. Yeah. Any other questions for the entire lecture or?
What about domain generalization for generative problems?
For generative problems, there are not too much domain generation problems, but in cases you have multiple domains, you want to generate, for example, some images in one domain and some images in other domains, you can also apply some domain generation problems directly to change the backbone of the generative models. But there do not have too many advanced technologies to apply this. Any other questions?
So I'm not sure if I missed this, but how do the interpolation techniques generalize to text data?
Yeah, we can go back to this here. So this is for the image data.
Yeah.
For the text data, if you want to apply the mix-up, we will change it to text, the input to text, and the feature extraction would be sometimes BERT, and you will get the feature representations. You can treat this feature representation as another kind of input. Yeah, and to apply interpolation here. Any other questions? Okay, if we do not have any other questions, so there are also some reminders. So the project milestone on Wednesday. And the next time is lifelong learning. Lifelong learning is something to combine the techniques that we learned before. So hope you can enjoy it for the next time.